This planning tool, implemented as a guide for surgeons before a tumor resection, disposes of a viewport on the left side, which contains a possibility to switch between different view modes as well as a selection mode, which will be distributed later. On the right-hand side, a slicing panel is implemented, of which the functions will be shown in the next section. Beneath the slicing, a modality list is located, out of which the surgeon can choose the structures of interest. Below the modality list, a panel corresponding to the picked modality is situated and an overview of functions is given. In the following, the video is categorized in two parts: exploration and surgery planning, beginning with the exploration. By enabling the conventional plane slicing, the surgeon is able to slice the T1 weighted image from 6 different angles in order to view the structures inside the skull. Via switch to the tab 2D Slice View, the surgeon has the possibility to have a look at the underlying images from a perspective that is commonly used and may be to his convenience. Besides the surgeon's amenity, this aspect allows a selection of additional regions. In the 3D Standard View, the result of the selection can be seen by slicing the T1 weighted image further. The T1 panel contains of several functions, of which one is showing the distance between the tumor and the previously marked T1 region. The distance measurement can also be computed between other structures of interest and is always displayed beneath the viewport. A second slicing possibility, the so-called cavity slicing, by which the user is able to view the tumor and adjacent structures through a cylindrical cavity, of which the radius, depth, and smoothness may be adjusted. The view of cavity slicing is always centered on the tumor, indifferent to the viewing angle. By freezing the orientation, the slicing cavity is set to a fixed position. Adjusting the smoothness enhances the view on anatomical structures as well as the depth perception when looking from the outside. Loading vessels, activation areas, and the perifocal edema to the sliced T1 weighted volume provides spatial distribution of the tumor's position. A whole brain fiber tracking was computed by using all voxels above a specified fractional anisotropy value as seed regions. Further subsets are extracted by the application depending on the question, or manually by the user. For example, fibers crossing an activation area, the tumor, a user-specified volume of interest, or a defined access path. Each of these modes is adjustable in their color settings. Additionally, more specific fiber information can be explored. Fibers crossing a critical region surrounding the tumor can be adjusted by increasing or decreasing the critical region. A box which can be adjusted in size and position defines a volume of interest and displays fibers crossing the specific region. Via this function, the surgeon can select more possible critical regions such as the visual and language system, of which he might have to be considerate. By marking regions of the activation areas, the surgeon can view all fibers associated to his selections. Wrapping one or more bundles of fibers to avoid visual cluttering may give the surgeon a perception of actual fiber tracts and their spatial relations. Before the actual path planning, the surgeon has the possibility to display potential risk structures, such as the activation areas and tumor, with each of their corresponding fibers as well as vessels. Setting a path can be achieved by simply clicking the button Set Path. A half-transparent brain mask emerges, which functions as a sphere on which all accessing points for the following procedure are defined. To evaluate different path settings for finding the most adequate access, markers can be set. Defining the entry point of the access path on a 2D projection of the skull comprises ambiguities and weak precision. Therefore, an innovative separate view from inside the tumor center is given. Looking from inside the tumor, the user can see all properties of the brain that lie between the head surface and the tumor itself. In addition to the orientation guide visualized as a skull, 3 orthogonal-oriented rings colored in blue, red, and green provide better orientation to the surgeon. Inside the tumor view, the surgeon has the possibility to set an access path as well, and to mark the selected point on the head surface. As seen from the outside view, the path is enclosed by a cylinder, which is divided into rings. The radius of the cylinder, as well as the separation of the rings, can be adjusted manually. For each path, the crossing fibers can be computed and visualized. The set markers can be addressed individually, and the associated path is displayed with its corresponding crossing fibers. If desired, the distance between a path and the chosen structures can be visualized using a color encoding, where the color of parts that are further away from the path fades. This distance-related color encoding can be used with fiber wrappings and vessels and potentially adjusted manually. The markers defined by the surgeon are positioned on the head surface to indicate the entry point. To provide a surgical view of the final access path by means of adjusting the smoothness, radius, depth of the cavity slicing, the surgeon gets an impression of the three-dimensional spatial information of the structures with respect to the chosen access path. Finally, the planning procedure can be saved as presets for further evaluation.